Coming to the lecture series. I'm Andrew McCloskey, and I'm the manager for the Biostatistics component of the BBSR, and then Andrew Goodspeed's also on here, and he's the manager for the Bioinformatics component. And today, Dr. Kathleen Torkko is going to talk about using Prism to perform ANOVA. Just a little bit about Dr. Torkko. She has a doctorate in epidemiology. She has extensive experience in developing databases with the pathologic, clinical, demographic, and other outcome data. What she really excels at is linking these with biospecimen data using sources you may be familiar with, like Health Data Compass and CoPath. Right now, she provides biorepository support for our component by helping to identify cohorts that investigators can use for like the tumor registry data, ENCORE, and so on. So yeah, I'll turn it over to you, Kathleen, and look forward to the presentation.
Okay, for the what I call the real statisticians, this is going to be probably a nice little stroll down memory lane of the ANOVA. Let me share my screen before we go on, and I'm not going to put it into full screen display mode for that. I'm going to keep the you can see my slides here. It's just that when I do that, it's like everything disappears in my computer screen. All I can see are my slides. If you have any questions, I know that chat is there, but I tend to ignore chat when I'm lecturing. So there aren't a great number of us here, so just unmute and ask your question. I don't mind at all if you interrupt me mid-sentence. That's no interruption. I appreciate any and all questions. Okay, let's get started. Yes, today is going to be more of a practical review and also application of the ANOVA using Prism. GraphPad Prism is a program that's widely used by the basic scientists and other scientists and clinical such in the campus. I work primarily with basic and translational scientists, and I teach the class for the elementary, or not elementary, introductory statistics for the graduate students. And when I took over that class, the best way to learn something is to teach it. And when I got to the ANOVA lecture, there's a very important concept in the ANOVA, the between and within variation, that, to be honest, and I apologize to my statistics teachers, I didn't really pay any attention to and didn't quite understand. I'm explaining the eureka in the corner of the slide here. What happened when I was trying to teach this ANOVA to my class, I sat down and thought, okay, gosh darn it, I'm going to learn what this between and within variation really means. And I was sitting at my desk and I went, eureka. Now, if I'd been Archimedes and I'd been in the bathtub and I discovered the law of displacement and ran out of the tub saying I found it, but I didn't. I didn't even run down the hallway, but I was very happy that I actually finally understood what between and within variation means. And we're going to go over a little bit of that today. It'd be my wildest wish that we'd all have our eureka moments, but I'm kind of a nerd, and but I hope you will learn to appreciate the ANOVA is actually a very elegant test. Now, before we get started, I want to issue a disclaimer. I just Googled disclaimer and this little picture came up. This lecture is not meant to turn you into statisticians. This lecture is meant to let you have an appreciation of what to do, what the ANOVA is, how to do it appropriately, and how to use Prism to do that. I think it's very important that you understand that, because I think it will help you plan your data collection and better understand how the analyses are done. Also, when you talk to a statistician about your data, it gives you more common ground to do that. And plus, you can run preliminary results through, but I would highly advise that you, if you're going to apply for grants or write papers, that you seek out a friendly statistician to help go over your work and make sure everything is as it should be. So today we are going to talk about how to do an ANOVA appropriately, talking about the assumptions of the test, talk about how you can evaluate the assumptions using GraphPad Prism, how to perform and interpret an ANOVA using Prism, and then get into, at the end, a bit with the non-parametric equivalent, the Kruskal-Wallis test. So when I teach my class, I always try to get my students practice on what happens when you have data. When you take a statistics class, you talk about the t-test. You're given data sets to do a t-test. You don't really have to think about it. When you collect data, and you might, in the real life, you go, wait, what kind of test am I going to use on this data? How do I know which one to use? And you can have, there are a lot of decision trees like this one. And usually the first thing you do is you want to decide, is it continuous data? Usually that we say quantitative data here, but continuous is a special type of quantitative data. And it's kind of in the vernacular where we talk about continuous data versus categorical or nominal data, which is a whole nother set of statistical tests. So if you have continuous data, and I think we know it when we see it, it's data with decimal points, it's like weight or age, anything kind of numeric data then would fall into this area. And then you make a decision about, well, what is the shape of the distribution of my data? And this isn't the only thing you use to determine between parametric and non-parametric tests, but you look at distribution and data variation and such. And then you make a decision from there. Am I only comparing two groups? Say, for example, I want to see if tumor volume varies by whether you have, or maybe days survival, that might be better, whether you have a low grade or high grade disease. And that if you have two groups that you want to see how days of survival differ, you would then use a t-test, go to the family of t-tests for that. But if you have more than two groups, say you want to compare days of survival by whether you have low risk, moderate risk, or high risk disease. And then you would then, in that case, use the ANOVA. And today we're going to actually talk about the one-way ANOVA in particular, and then its non-parametric equivalent. If your data are skewed or have outliers, you can't meet the assumptions, which we're going to talk about, of the ANOVA, then you would use the Kruskal-Wallis test, or there are other choices like data transformations, but we'll go into that in a little bit. So the basics of the ANOVA, if you're starting out with your data, you're going to have one continuous variable, say like tumor volume, and you have one categorical variable that has at least 3 levels, 3 or more. If you have only 2, say you're just looking at placebo and drug 1, then you would do a t-test. But if you have placebo and 2 drugs, drug 1 and drug 2, and you want to measure tumor volume, how it differs between those groups, then you would do a one-way ANOVA. If you have 2 categorical variables, as an example, say you have type of treatment and gender, you have a suspicion that maybe the tumor volume by treatment will differ by gender, you can then do a 2-way ANOVA or some other multivariate analyses. And that is a totally and entirely different lecture that I could give in the future, perhaps. Okay, so here I just went online, and actually I go to Nature. I use Nature a lot when I'm searching for examples to teach in my class, in part because of the basic science nature. But also Nature is kind of in the forefront of rigor and reproducibility, and they require their authors to provide data when they have their papers published within the journal, or at least provide access. In some cases, you just have a disclaimer. The author will say, reasonable requests will provide data. But it's nice to go in there and actually find the data sets attached to the data, and you can use these as examples. But I just use this one here. I searched for COVID papers to be topical, and this was a paper where they performed an ANOVA, as they said in the figure, where they're looking at a continuous variable, which was their antibody binding. They're looking at IgG and IgM, and then looking at 6 different groups, looking in here particularly at increasing doses of the vaccine, and looking what the immune response was to these. And they did an ANOVA, and after that, although they didn't state it in the figure, and I'm sure in their statistical section they stated, they did some sort of post hoc test where they were to compare 2 by 2 where the differences lay between the 6 groups. Now, I don't think this is the best figure. It's rather busy, but it was the one that actually came up first when I did my search. But today I'm going to use an example from another recent paper. This was published in Nature in December. And I'm not going to talk about the science. I put the abstract here, and it's about the creation of bladder assembloids. I just thought that was a rather interesting word. But what I was more interested in, if you have an interest in assembloids, by all means, have a look at this paper and the science. And I'm not here to judge the science. I'm here to judge or to talk about the statistical analyses they did in their paper. And specifically, I'm looking at figure 1B, which is the figure 1 is generation of 3D reconstituted bladder assembloids. Figure 1B being the quantification of epithelial and stromal cell proliferation as measured by a mitotic index in these bladder assembloids. They explain the error bars as and the measures of effect as mean and standard deviation. They show bar graphs here, where the top of the bar graph is going to be the mean of the data. And they also show the individual plots of the data. They have 6 animals in each group, I believe. And you can tell right away this is a Prism graphic. They have a very specific recognizable characteristic, but I can also tell by the fact that the authors reported their p-values to 4 digits. I usually don't need to do more than 2. Well, in this case, you would report to 0.0002, but here I would have rounded this up to 0.01 and 0.02. People get very enamored of this high, statistical, reporting it to a higher level of digits. I guess you don't really need to do that. It's not that meaningful. And I know it's Prism because Prism by default always reports it to 4 decimal places unless you ask it not to. So here we have the sample sizes and numbers and such are in the statistical section, which we'll get into. But the different groups here are DMSO, which is more control, but they're looking at pharmacological manipulation of the hedgehog pathway using either an agonist, SAG, or an inhibitor. I'm going to call it V because these names I use for drugs are, I don't know who came up with these kind of odd names for drugs. But I want to go back to the good old days. So we're going to talk about focusing on the epithelium part of that graph. And actually, let me go back. This would have been ripe for a 2-way ANOVA analysis, but they chose to present them as individual analyses. Maybe I didn't look in the paper, maybe that was their hypothesis, but they could easily have done a 2-way ANOVA because they had the categorical variable of the pharmacological manipulation, the drug, and then also the categorical variable of a cell type. So they could easily have done a 2-way ANOVA on this, but today we're going to use it as an example for 1-way ANOVA, and we will be focusing on the epithelium. And if we have time, I do have data on the stroma as we go through. But back in the good old days, I remember talking to an older researcher who said, we never used to put p-values on graphs. We just would do a graph. I reproduce the data in a Prism graph here. And you used to look at it and say, yeah, the mitotic index goes down with the V group and it goes up with the SAG group. You didn't have to attach a p-value to look at that and say, yeah, this could be important. This is a demonstration of some biological relevance. And I actually, to show that, this is over time, this is in the last 50 years, I just did a quick search in PubMed where I searched on P for every 5-year period. And you can see there's been an exponential increase in the use of P equals whatever. So it is becoming increasingly required. I don't know if it's increasingly important that we always have p-values attached to things, but journals are requiring that you do these statistical tests, and they do add a piece of evidence in support of your hypothesis. But in some cases, I think maybe the good old days were just as good, but we do require statistical analyses, and we'll go on how to do this ANOVA. So here is from their data analysis, where they said they carried out statistical analysis using GraphPad Prism. Okay, I had already figured that out by their graph. We presented all data as mean plus standard error of the mean, and that's another lecture. Is that the correct kind of error bar you should use or not? And we performed comparisons between groups using 2-tailed unpaired t-tests. Another hint that this is a GraphPad Prism analysis. Prism calls it unpaired. I always learned it as an independent t-test. but values of P were less than 0.05, were considered statistically significant. They could also have said their alpha was set at 0.05. But so we've got a little bit, this is not a very detailed analytic section, but we've got a little idea of what they've done. But I'm wondering, did they really do a two-tailed t-test on what is obviously data that looks like it should be done using an ANOVA? And in fact, they actually did. They did for figure 1b to two-tailed unpaired t-test. Okay, now I think about that and I go, okay, this automatically raises red flags to me. Why did they do a two-tailed t-test? Why they do t-tests rather than an ANOVA? And it also looks like as comparison, they were only interested in comparing the two treatments to the DMSO group, which is fine. But they did two t-tests rather than one ANOVA to help look for differences. And this brings up a problem of multiple comparisons. There's a problem, and those of you who do big data experiments where you're looking at hundreds, if not thousands, of different factors that you're trying to determine if they are significantly different, you run into a problem of a lot of false positives, and you have to worry about false discovery rate, because you can find, if you have a lot of comparisons, you can just by chance come up and find that things are statistically significant in your analyses, but don't really have any kind of biological or clinical, or you could just find false positives and not realize that you are finding a false finding. So you really need to worry about your type 1 error rate, that is your false positive results. You can't ignore the alpha, because what happens when you want to keep your alpha, your error rate at 5%, which is by convention, and that's another lecture we could get into, is why we have chosen 0.05 as something that is important or not. But when you set your alpha for your studies as your false positive rate, is that you're allowing a certain amount of error in your analyses. We can't set our error to 0, because 0 in mathematical equations just blows them up. If you get 0 in the denominator, you can't get an answer. It's nonsense. So you have to allow a certain amount of wiggle room. And by conventions, that's set at 0.05. But that then opens you up to errors. And specifically, we'll focus on this talk about the type 1 error. For example, you want to limit the number of elderly men, you're telling them that they're pregnant. That's obviously a false positive result in the data. And conversely, you don't want to start reporting that things are statistically significant, where it was done just by chance or by errors, and that you did multiple comparisons and your false positive rate was blown up. You want to try to keep that controlled at 0.05. So what we'll do then, when you do one test versus two tests, you start to get into that area. Now, this isn't going to be a big difference, but there's some cases, I said, where you can do maybe 5, 10, or hundreds, or even thousands, but you want to try to make sure that you're doing the appropriate test to help control against the possibility of doing multiple testing. And so we're going to do, instead of as they did, a two-tailed t-test. So they did two t-tests rather than one ANOVA to look at these differences in the mitotic index and epithelium. But let's do an ANOVA instead. So what the ANOVA is doing, the one way, is a test of means for more than two groups. And it tests an overall effect. It's called like an omnibus or global test. I tend to refer to it as global. And what it does, when you get a p less than 0.05, if you've set your alpha at 0.05 and your level of significance is less than 0.05, it will say there is a difference between at least one group and another group. It won't tell you which one. And what this does, it avoids the level of multiple testing. You've got one test that will say, yes, there is a difference. It uses the entire sample size of your data set. And what you do, if you do get a significant result in your ANOVA, you go on and do post hoc tests to determine which groups differ from each other. And these post hoc tests do it by controlling the alpha rate. So your error rate doesn't go above 0.05. Here's the data from the publisher from Nature. The author included some Excel where they have the source data here for, this is figure 1b. And here's the epithelia group and the stroma group, and they have the DMSO, the V group, and the SAG. And here they divided Ki67 by DAPI and created the percentages, they're calling their mitotic index. And this is the data then for this bar here, and so on. So what I do is when you have particularly a small number of data points, I just do a copy and paste out of here directly into Prism. I find that to be the easiest. I'm a PC user, so I just do a Control-C and a Control-V to get the data in. There are more sophisticated ways to import your data, particularly if you might be dealing with larger data sets, but I won't go into that today. That is another lecture. So what we'll do is when you open up Prism, you start with this pop-up that shows you that first thing you have to do is decide which table you're going to use for your data analysis. I know that column is where I'm going to do my one-way ANOVA. But if you're not certain, so when I do that, I know I'm going to go and I'm going to start entering the data. This is what I use. I'll hit create. But if you're not sure, if you're a little worried, like, well, I'm not sure, is it the XY, the grouped, or which one do I do the one-way ANOVA? Just go down here and start with a sample data set for follow a tutorial, which is a very handy feature that it will then drop down, and then you'll see right away, okay, here is the ordinary one-way ANOVA or repeated measures ANOVA, one-way ANOVA. And you know, okay, this is the right table for that format. And if you say, well, gee, I forget how to put the data in the one-way ANOVA, you can hit create. And here it gives you a table. It fills it with some data, and it will give you explanations about it, and you can go through a tutorial to do that. Now, one thing that I don't like about Prism is that you can see that you have your different treatment groups have to go into separate columns. In most other ones, I'm a SAS user, so I started using, you would have a column that had your category, your continuous variable in it. Let's say this is age. I don't know what these data are, but say it's age. And then you would have an indicator variable in another column that would say control is a 1, and these all would have a 1 next to it. These would all have a 2 for treated next to it in the column, and these would all have a 3 for treated plus antagonist. And then you would just tell the program to do an ANOVA on the continuous variable by treatment group. But with Prism, you have to already sort, and you have to put the data in already sorted by treatment group or whatever your group you're analyzing. And that's a little tedious and not, to me, the best or the easiest way to get your data in, but it's just one of the limitations of Prism. So I went in already and I created a table, and it's always important that you name your table. So if you go back, you can look and know exactly where your data are and what it relates to. So I have figure 1B epithelium, figure 1B stroma. You could potentially put them in the same column, but it's easier when it creates graphs and things to do it separately. I also looked at figure 1F. If we have time, we'll look at that. So I copied the data under the DMSO, the V, and the SAG groups. Now, before you do the ANOVA, now you could just go to analyze and ask it to do an ANOVA right away, but you really need to understand your data and see if your data actually do match what you want to. Do they meet the requirements of an ANOVA? And one of the best ways to do, and you should always do this anyway, when you get some data, particularly if it's not your own data, is look at it. Is there anything that looks odd? Graph your data. Are there any data that are outliers? And when I say outlier, I don't mean that it's data you have to automatically delete because it's 2 standard deviations away from the mean of the group. It could be a data entry error. It could also be real and interesting data, and it's not something you necessarily want to delete. But one of the things you can do first is look at descriptive statistics, and also you can graph the data, which we'll get into. But first, I want to go into the assumptions of the ANOVA. 3 main assumptions, and these are also similar for the t-test, is normality, homoscedasticity, it's all equal variances. It's a wonderful world, homoscedasticity. Its opposite is heteroscedasticity, and I defy you to, I challenge you, I should say, to use those words in polite conversation at dinner tonight. You'll wow your friends and family. And also independence. Actually, independence is probably most important. The ANOVA and t-test are actually robust tests. They allow some deviation from normality and equal variances, but independence is a very important point in the data, that if your data are not independent, you will not be using an ordinary one-way ANOVA. You will be using some test that allows for the data that are dependent. For example, independent data has to be, it's easy, like if you're doing 6 different animals, you'll have 6 different measurements. You'll have independent data. If you do 6 measurements repeated over time in the same animal, those are dependent data. Those are more repeated measures, and you would use a different analysis protocol to do that. But let's talk first about normality, but maybe think it more as symmetrical distribution, because in reality, the true concept of true normal distribution is a little bit of a golden unicorn. It's a mathematical perfection that real data rarely meet. But what you think of with a symmetrical distribution, and here this is a standard normal distribution, bell curve, where the mean and the median are the same. Also the mode, which is the most common variable, are here at the top of the distribution, the most common. And as you go out, as you go further out, like say this is height, as you become taller, it becomes rarer to be taller. And also for very short people, it's rare. So the distribution is clustered around the mean. The mean and the median and the mode are all the same values. And so that's one way you can tell. If you look at a tool I use to look at data, I'll look at when I get descriptors of the mean and the median, I'll see, are they similar? If they are similar, then I'm getting an idea that the data might be symmetrically based. But usually, here's some real data. These are heights of winter and summer Olympians, Olympic athletes, and the winter in brown. And the first time I looked at it, I said, boy, those winter athletes are short, until I realized this is a frequency distribution. And in reality, here's the height down here, and they're the same height. It's just that there are far fewer winter Olympians. So their frequency is smaller. That's why these bars are smaller. Not every country is able to have snow to allow to have winter athletes. But you can see this is a large number, and you still have, it looks symmetrical. I suspect they might have grouped men and women in this graph, where you might have 2 peaks here, where there's a slight shift in the distribution for men here compared to women. But overall, I would accept this as a symmetrical distribution and would feel very comfortable doing an ANOVA or a t-test on this data to meet the assumption of normality. So the data needs to be approximately symmetrical, normally distributed, but an ANOVA is robust to deviations from this, particularly if you have a balanced design. That is, if you have equal numbers of samples in your different groups. And if you have skew, if they're all positive skew, if they're skew out in this direction in all groups, then that would be okay, the distributions are the same. And again, deviations from this are less important if you have large sample sizes, say over 30. If you have small sample sizes, like I do deal with in a lot of basic science experiments, it becomes a little bit more problematic to look at. So here, actually, when we're talking about distributions, the ANOVA actually looks at the residuals. And this is just a brief explanation of what the residual is. And what it does is it normalizes the data. It looks at the differences. It calculates the mean, and it looks how each of the data points within that group are different, how variable they are from the mean, how they deviate from that group mean. And so if you calculate that, if I were then go in and I did that here, I calculated the residuals by subtracting every point from the mean of the group, and I plotted that, they're exactly the same distribution as you would have just looking at the raw data. There's just a different y-axis to it. It's been normalized. So each group is on the same scale here. But in order to assess distribution and normality and such, looking at standard deviation, you can use the raw data and don't have to calculate residuals to do that. So for homoscedasticity, you want to eyeball a lot of the work, and statisticians, there are formal tests you can use to say, are the variances equal between these groups? Are they different? But these tests are prone to false conclusions based on sample size. They don't work well in small sample sizes, or they don't work well in very large sample sizes. So a lot of statisticians, when they do assessments for tests, they're going to eyeball. They're going to look at the distribution. They'll plot the data. They're going to look at things like mean and median. They're going to eyeball the standard deviation and say, okay, I think these data are fine. And everybody has their little different way of doing this. I have a rule if I'm looking at just the standard deviations comparing the groups. I use what I call the less than 2 rule, which says basically you look at the standard deviation for each of your groups and you divide the largest standard deviation by the smallest. And if the standard deviation is less than twice the size, the largest from the smallest, then you can assume that we will assume homoscedasticity, and that data variation will not be a big problem, particularly since we know that the ANOVA is robust to deviations from some data variability. And we already went over independence, but that you're categorical. So each group must be, you have to have different, measuring different animals or different people in each of your treatment groups, for example, and also the data within each treatment group. The individuals or the mice have to be different in that so that you have independence. So what you start with to get your data description, you went to analyze and you had that ask for descriptive statistics, and this little box pops up and you can make your decision about what you want to do. I want to look at median and the mean and the standard deviation. And also I look at skewness. These describe the shape of a more normal shaped curve. Skewness, as it says, tells if the shape is more skewed either positively or negatively. And kurtosis, which I don't really use, it's more about how tall or flat the shape of the bell curve is. I think it can still be symmetrical no matter how tall or flat it actually is. So I'm going to run that to get these to make my first assessment. So here is the result of the table, and it's for the figure 1b epithelium. In the groups, it's a balanced design. We have 6 in each group, but it's small. This is a small sample size. Let's look at the difference between the median and the mean for each group. So median here is 26.9, very close. I'd look at that and think, the data probably are pretty symmetrical. Let's jump over to SAG because I already know the results. This is 49.8 and here's 49.2. Pretty close. There's some evidence of some positive skew because if you have a data point or your data are skewing out into the larger direction, the positive direction on the graph, that it will pull the mean over. It will follow the direction of the skew and it will be larger. It won't be quite the same as the median. But let's look at the V group. And this is 0.97 and 2.7. Okay, there's quite a difference here. So I have some concerns right now about whether the data meet a symmetrical distribution. Let's look at the skewness then. Here we have some positive skew. We have strong positive skew in this group, and we have negligible negative skew. And looking at this, you can say if it's less than, this is either less than 0.5 or greater than negative 0.5, then you can say it's minor to no skew. If it's between 0.5 and 1, you have moderate skew. And if it's greater than 1, you have significant skew. So this will give you some indication. This again is telling me that we have different skew in the data. So again, we may not be meeting the symmetrical decision. If all of them were, say, had a skew of 0.45 or similar, then I probably would, or even 1, but all positive 1, I may not worry as much about skew. But here we have strong skew, and here's just a little bit of a negative skew. Now, as far as standard deviation, to look at the homoscedasticity, we see using the 2 rule that here, this is about over 3 times bigger. So, and this is about half. So we do have evidence that there is heteroscedasticity in the data. So it looks like even though we have a balanced design, which is good, we might have some problems applying an ANOVA to these data. Now, another way to assess it is to do graphing, and I highly suggest you graph your data before you do analyses, even if it's your own data, so you can help you assess the distribution and spread. So you can go up when you're on the table, go up here and ask to do a new graph of existing data if you hadn't already done it, and do a box plot, which I do I find useful because the shape of the box plot and how you can look at that and get an idea of how symmetrical the data might be. If the whiskers, these go from minimum to maximum values, and if these whiskers are about the same length and kind of, this represents 50% of the values, and this goes out like 25% on either side. Then you would have a symmetrical distribution. Also, if this bar in the middle of the graph, which represents the median of the data, if it's in the center of the box, these two I would look at and eyeball and say, I think these are pretty symmetrical. And I think that also was what we saw within the descriptive data. This one is the problematic one. We seem to have a right skew, a positive skew here with this one bar. Now, another way that you can look at the data is do univariate scatter plots. You can also plot the data over the bar graph, the box and whisker or bar graphs. But a lot of papers are saying if you have about 20 data points or less, that it's better to show individual values rather than some summary value. In this here, we have the median with the individual data points. And you can see this gives you an idea about how variable, that these are about the same variability as these. This one's going to have less variability, as we saw. This shows the right skew from this one data point. You might want to check if that potentially could be a data entry error or if it's real data. But don't automatically delete it because it's not like the others. It could be something that is important that you discovered. You can also do other plots that help, and frequency distribution plots are useful, not so much when you have smaller sample sizes, as I'll show. So you go into the analyze when you're in the table, go to frequency distribution, have all your ones, unless you want to do them individually. If you want to put them on the same graph, have them all checked. And you go down and you can do frequency distribution or cumulative. You can do numbers or relatives. You can choose your bin width or have Prism choose it automatically, but be sure to check the box if it's not checked to graph the data. And this shows then the different groups graphed. And this one looks to me like it's more symmetrical. So does this one, where more the majority of values fall in the middle of the distribution. There's a little bit of skew here, but this one is definitely skewed. You have most of the values here and that one value that sticks out further to the right. So putting it all together, I look at this, we have the different graphs. Here's the box and whisker plot with the individual values, the individual data points put over it. And based on all this, it's going to be a matter of opinion. What do you do if you find, I would tend to look at this and say, I don't think we really meet the assumptions. There might be other people who say, no, ANOVA is robust to this. We have a balanced design. It's a small sample size, yes, but the ANOVA is robust. So say that you conclude your data aren't normal. You have basically three things. You can transform the data, because transformation, like if you do the log or the square root, depending on the distribution of your data, and you can then get it to be more symmetrical. And also it's very good at minimizing differences in standard deviations. And then you can run your analysis on the transformed data, as long as you've transformed all the values in your data set. And then what I usually do in that case is I present the table, the real data, but I present the p-value and I explain that in the table that I used, the p-value was run on transformed data in order to meet the assumptions of the test. You can use the non-parametric test or equivalent, the Kruskal-Wallis test. There are issues with that, which I will get into towards the end. Most people would prefer to use the parametric tests because they have more power, they have more ability to detect differences. Even though the non-parametric test you can use it on any distribution really. It doesn't matter what the distribution is or what the variability are, it is robust against those violations. Or you can just do the ANOVA anyway, knowing that it is a robust test. And if you have equal sample sizes or you have large groups or the skew is in the same direction, you can make that justification. The point is here though, what you want to do is before you run your test, or even before you collect your data, you want to put in a statistical analysis plan to decide what you're going to do when you face a situation where you look at the data and you say, look, it doesn't meet a normal distribution. What am I going to do? Am I going to do everything and just find the result that matches what I want to find or gives me the smallest p? No, you really should go through and decide, I'm going to try data transformation. If that doesn't work, I'm going to look, or I'm going to do the ANOVA anyway because it's robust, or I'm going to transform, check if it doesn't work, then I'll do the the Kruskal-Wallis test. Okay, we'll get into that a little bit. But before we do our ANOVA on the data, let's talk a little bit about the bones behind the test. The ANOVA uses the F statistic, the T test uses the T statistic, and it's just the value that it calculates from the equation that it uses to calculate from the data. So what the F statistic does, it's really a ratio. It's using the between variability divided by the within variability. And here's where the between and within comes. The between variability is how variable the means are within each group, or between each group. The variability between your three groups. For example, if we're looking at the DMSO, the V group, and the SAG group, how different are the means from each other. And then the within variability is within each individual group, is how variable are the data points within the group. And the point is, with the larger the p-value, the larger the F statistic, the smaller your p-value. So the larger your between variability is between groups, the larger your numerator, the larger your F statistic will be. The larger the variability within the group, the larger your denominator, and the smaller your F statistic will be. So the name, the analysis of variance, comes from how it judges and tests the variability in your data. And what I have here in the bottom is, to scare you all, is the ANOVA table, which you've all seen if you've done ANOVA, and I'm sure you've all had a statistics class and done that. Here's your between and within variability. Is calculated by doing sums of squares between and sums of squares within. It's adjusted for a sample size. In a way, it looks at the degrees of freedom, where it takes a number of groups minus 1. So if you have 3 groups, your degrees of freedom will be 2. And the sample size of your whole sample, if we had 6 mice in each group, 3 groups, 18 mice. So it's 18 minus 3 groups. So the degrees of freedom would be 15 here, and we would divide what we calculate with sum of squares by 2, and here by 15, we get the mean, and the ratio of that is our F statistic. And let's go over that in a little more detail. So the heart of the ANOVA is the between and within variability. Here is illustrating the between the groups, where we're looking just at the means of the groups, and we see that there is a difference. And just eyeballing the data, we'd say, okay, whatever you did was effective in group 3. And there is a difference. If they were all the same, then we know that the test would not do, there's no variability. So this is going to be a very small numerator, and we're not going to have a large F statistic, and probably will not have statistical significance. But looking then at within each group, here are the data points that were used to calculate the means of the groups. And we see they can be quite variable. This could be just due to biology. It could be due to measurement error. It could be something that is hard to measure, like blood pressure varies and things, but you really do, this could be human error, but it also does measure biological error within the group. And if this is too big, it's going to overwhelm what we see within the between groups, because this is what we're really interested in our experiment, is how did our manipulation, whatever treatment we did or whatever our experimental procedure was, this is what we would expect to see, or what we want to see, that there is some difference. But it also is going to depend on how variable the underlying data are. So here I'm getting to my eureka moment. So when I realized that, okay, all it is just looking at the variability. So the bigger the difference between these means of the groups, the larger your numerator, the larger the F statistic, more likely to be statistically significant. But the more variation you have, or the less variation you have within each group, is going to mean, with less variation, a smaller denominator, a larger F statistic. That's why when you see here a P of your ANOVA test is highly significant compared to, in this case, you would say our data do not support a conclusion that there is a difference between the groups. So this is where I got my ANOVA, was that this is just a very elegant and very simple way. Whoever thought this up was a genius. And I had my eureka moment in trying and finally figuring out what between and within variability meant. So to calculate, just briefly to go over the sums of squares for you math nerds there, graphically what you do is to do the sums of squares. And what it is, it does some squares. What you do is you do a grand mean, where you calculate what the average, what the mean of these 3 means is, and then you subtract the mean, the grand mean from your data from the mean of your data from the grand mean. And you then square each of those because you're going to have in some cases a negative value and you don't want to sum negative and positive values. So that's why you square them. And when you sum all of those, that becomes your sum of squares between. The sum of squares within, it's a little hard to see here, but what you do is it's like you calculate the residuals. You're going through and looking at how each of these data values are different from the mean for that group. And again, you sum the square of each of those differences and you sum it across all the groups. You do it's all put into one sum of squares within. It doesn't do it by the individual groups, but it just groups all the data in and makes that sum of squares within. And so then you do the calculation, the 3 groups minus 1, you divide that sum of squares between by 2 and so on and get your F ratio. And this is why it's important that you have homoscedasticity in your ANOVA, is because if you look at this distribution of the data, I think if you were to compare group A and group C, that I'm sure you would get a p-value less than 0.03 and declare, given that they don't overlap. These are going to be different. And the variability is very low in these groups. But for some reason in group B, you had a great amount of variability. And the ANOVA just sums the variability over all the groups. And so you might come up with a negative finding. You might get a p less than 0.05 just because one group was so much more variable than the other, and it will overwhelm the values of that. There is an adjustment in the analysis you can do for that, but this is why looking at homoscedasticity is important when you're trying to determine if the ANOVA is appropriate. So what we're going to go ahead now is we're going to run the ANOVA on the data, and I better go quickly. I'm running out of time here. So you go to Analyze, you ask to do the one-way ANOVA. You have all your boxes checked. If you just had 2, it's going to tell you, you sure you want to do the ANOVA? You should do a t-test, but we have all boxes checked. There's no matching. This is independent. We're going to use the ANOVA. Here's where you would check if you want to do the non-parametric test. And we're going to use the ordinary ANOVA, or you do have the adjustment you can use. This would allow you to allow different standard deviations in the data. We're going to assume equal variances now, just the standard ANOVA. For our multiple comparisons, we're going to ask it to compare the mean of each column to the mean of a control column like they did here. We're going to ask it just to compare to the DMSO. And as far as the other tabs that you got for the analysis, you have options where you can, I'm not going to go into them. There is a multiple comparisons test. I usually go with what Prism recommends because it usually is right. You can change your significance level here. Here's the 4 significance. Also with the residuals, these are more sophisticated ways that you can look at whether your data have equal variance, whether you have normality. I'm not going to go into those right now. I don't have the time in a 1-hour lecture, but here is the result then. After checking those, here's my ANOVA result. It gives a summary. We found a p of less than 0.0001, so it is a significant result. Here in the ANOVA table here, here's the sum of squares between, the sum of squares within, the degrees of freedom, and it calculates the mean square, which then the ratio of that is 37.11. And when you usually report a statistic for the ANOVA, you report the F statistic with 2 degrees of freedom for the number of groups and the 15 for the sample size and the value of that. And it used to be you'd look up at a table with these parameters and you come up with a p-value, but Prism and other statistical programs will calculate a more exact type of p-value. And what it's saying is with this p-value mean that there is at least one group different from one other. With the multiple comparisons test, you get in the tab here, it did a Dunnett's multiple comparisons, and it tells you that, yes, it's below the threshold. When adjusted, it gives you the adjusted p-value. And then the point is here, though, that when we come up doing the appropriate test rather than the multiple t-tests, we come up with the same conclusions. Although you notice the p-values are slightly different from what we have here. This one's a little higher, this one's a little lower. but we come to the same conclusions. But it's possible you may have come to a different conclusion depending on the data if you've done the multiple t-tests rather than doing the more appropriate ANOVA. Here I just did the t-test to show you where they got the p-values. Here's the 0.0002 and the 0.0055 that they reported. If you assume unequal variances, you can ask to do the Brown-Forsyth test, which here's the result. The Brown-Forsyth test you usually would use over the Welch's ANOVA when you have skew in your data, but both say that they come to the same conclusion as when we assumed equal variances, that there is a difference in at least one group. And here is the multiple comparisons test for the assuming unequal variances. Again, the conclusions are the same. Here's the results from the equal variances. The p-values are slightly larger here. And what I would say is that this is the one I would use because we do have unequal variances, and I would report this data. I would not, I would have my plan in place and say what I would do if the variances run equal and use this adjustment to that. And I would report these values as being the least biased test. Now for the stroma results, I looked at the data, and I'm not going to go over this in great detail right now, but you can see the standard deviations are quite different. There is some skew and some differential skew. This is moderately negative skew. This is moderately positive skew. So I think even more so than the epithelial results, these seem to not really fit the ANOVA test. Excuse me. I ran the test doing equal variances and equal variances. And the thing is, you do come up about the same conclusions, which variation of the ANOVA you ran as a demonstration. I don't recommend you do this. You choose the one you're going to do based on your data. But you see, we come to a different conclusion, though, from what they did in their graph. For their stroma, they said there was a difference between the DSMO and the DMSO, sorry, and the V group. But in our data, it said it was not significant. Now you could look at this and say, well, is this a real difference? You know, is this something that's important? But are we misleading them if we use a t-test and it's telling them that it's significant? Or is this something that's going to go against our hypothesis? You know, you want to look at the measure of effect. You want to see what's happening in the data. But you know, you really do want to use the appropriate test. So I would report this test, or I would use the non-parametric Kruskal-Wallis, depending on what your analysis plan was. And for the Kruskal-Wallis test, when you can't meet the assumptions of a one-way ANOVA, you can use this. It still assumes the observations are independently sampled and the groups are independent, but you can have skewed data and you can have data that have different variances in it. But it is also a little bit hard to interpret because it's really testing the rank distributions for greater than two groups. What a non-parametric, the Kruskal-Wallis test does is it takes all the data, puts it in one column from every group, and it ranks it from 1 to 18 in our sample, from smallest to largest. And then it breaks up into the three groups again, and it compares the distribution or what the ranks are. And you can have a Kruskal-Wallis test that is significant, because most people report medians of the data, which I do if I run a Kruskal-Wallis, but you can have medians that are exactly the same in a Kruskal-Wallis test that is less than 0.05. And that's just because the rank distribution, maybe one was strongly skewed to the right and one was strongly skewed to the left. But even though the medians were the same, because you had different distributions of the ranks, you had a significant result. And it is a global test like the ANOVA, and it will tell you if one group is different. And you also would then need to do post hoc tests. So in the menu, you go down here with the no matching. If you're going to run the Kruskal-Wallis, you ask for the non-parametric test, and it tells you do the Kruskal with the Dunn's multiple comparisons. Here is the result. We came up with the same result. This is on the stroma data. Here I have the Brown-Forsyth test for the stroma data of a 0.001. This came out with a bit of higher, but the conclusions are the same, even though the p-value is smaller here. You do have a case where you have a significant result. So you say there is at least one group that is different. So I ran a post hoc test, and when I did the comparison, neither of them came up as significant. Now the problem is this will happen, and this does concern people when it happens. But here you have sometimes what happens is the global test when you're doing the ANOVA or the Kruskal-Wallis, they're actually asking a different question from the post hoc test. Plus the post hoc tests are using different sample sizes. They're doing pairwise comparisons. So you've got 6 versus 6 rather than the global test using all 18 samples to do that. So you can get some contradictory results. But what I'm thinking that the significant result for the Kruskal-Wallis test was really driven by this result here between the V and the SAG group, which is a much bigger difference than between the DMSO versus the V or the SAG group. So, but we were only doing comparisons between the DMSO and the other two. So that's why in this case, we found out there was not a difference between the groups. So in summary, and I'll do this quickly, the ANOVA is an elegant test, and between and within is not really that difficult to grasp. It's up to you when you do an analysis to do the least biased analysis that you can. Have a statistical plan in place to decide what you're going to do when you're faced whether the data are normally distributed or not, or have unequal variances. What do you do next? Be transparent what you've done and explain what you did and why you did it. Always check your test assumptions, avoid your multiple comparisons, and always ask a friendly statistician to help you with this, particularly when you're going to publish a paper, apply for a grant. And the puppies are just there to give you a warm, fuzzy feeling after a statistical lecture. We have 2 minutes for questions.
Hi,
Any questions?
Kathleen,
Yes, hi.
I don't have a question necessarily, but I really enjoyed the talk, and I jotted down some notes about future talks that you had so graciously offered.
Oh, yeah, I'm happy.
Might have to bug
do.
you in the future.
Yeah, I'll do a 2-way ANOVA and a flash. I actually like it better than the 1-way.
Hi, Kathleen. This is Jack Nikoloff. Thanks for that talk. I had a question about an early statement you made when you were comparing the standard deviations between groups. And I understand sort of the basics of what standard deviations are representing. It seems to me, though, that your standard deviations are, one way to think about them is that they're some fraction of your signal size, right? So a quarter or whatever, if it's, or 10%. But in your example, your red data here in the middle.
Let's see, I'm trying to find that.
Yeah, any one of those would work here. The signal was so small on your middle points. And so it seems to me that the standard deviation is going to be, oftentimes anyway, relatively small. It's always going to be some fraction of your.
Yeah, I mean, that's.
Signal. So it seems like if you have wide variation, you're always going to have big differences in standard deviation. So I'm wondering if you could comment on that.
Yeah, I mean, that is true. You can have, I mean, it is going to depend on the underlying data. And as you said that, with that V group, they did have small mitotic indexes. They just didn't, I guess they didn't proliferate. And, but that still leads to the problem that you do have a difference in the variability of the data, which can affect your results from the ANOVA. So that's something that is biological, yes, but even though it's biological, it's going to affect the results of the test.
Oh, okay.
And you have to account for that.
I understand. Thank you.
Okay, I can go back to the puppy slide now. I want to thank you. If there are no other questions, thank you for listening. Sorry, it took a little bit longer. I kind of got carried away from a few stories, but I know it's a bit to take in, but I think that it is something that is a fairly important and I think an analysis that you can do on your own, and just as long as you make the appropriate plans and decisions on the data.
Thanks, Kathleen.
Okay.
Yeah, thank you, Kathleen.
Okay. No problem. Thanks. Bye. I'll stop sharing.